Okay, let's dive right into this explainer and solve what is honestly a pretty fascinating laboratory mystery. We're going to look at why water quality scientists will completely discard certain biological oxygen demand tests, BOD tests, when the oxygen in the sample runs out. I mean, it sounds totally counterintuitive, right? If you're measuring how much oxygen gets used, and literally all of it gets used, shouldn't that just be your answer? Well, the science of water testing is kind of more complex than that. So today, we're unpacking exactly how dissolved oxygen and BOD interact, and why we have these incredibly strict lab rules governing how we measure pollution. Here's our roadmap for today. First, we'll get a handle on understanding DO and BOD. Second, we'll walk through the 5-day BOD test. Third, we'll hit the 0 DO rule. And finally, we're going to troubleshoot some common test failures. But before we get bogged down in laboratory protocols, let's start with a really foundational question about the biological stakes here. What actually happens when an environment, like a local river or stream, is starved of its life source? Well, the consequences are absolutely immediate and they're severe. Fish, bugs, all those aquatic organisms, they rely entirely on dissolved oxygen to survive. When those oxygen levels just plummet, the water literally cannot support life. But that begs the question, what exactly is pulling all that oxygen out of the water in the first place?
Which brings us to Section 1, Understanding DO and BOD.
All right, so here is the formal definition straight from these standard lab methods. Biochemical oxygen demand, or BOD, measures the molecular oxygen utilized by microorganisms to degrade organic material. Now, to put that in plain English, BOD is simply the amount of oxygen that bacteria need to break down and, well, eat organic waste, stuff like sewage or agricultural runoff in the water. Dissolved oxygen, on the other hand, which we call DO, is the actual amount of oxygen available in that water. And these two, they're locked in a constant invisible struggle.
As you'll see here, this brilliantly illustrates that exact struggle. Notice the inverse relationship between these two metrics. In a healthy, unpolluted river, you've got really high dissolved oxygen and a super low BOD. We're talking typically under 1 part per million. So plenty of air, practically no waste. But look at untreated sewage. The BOD absolutely skyrockets to anywhere from 200 to over 600 parts per million. As organic pollutants pile up, bacteria basically feast on that waste. And as they eat, they multiply rapidly and they breathe. In doing so, they pull massive amounts of dissolved oxygen right out of the water, leaving absolutely nothing behind for anything else trying to live there.
Let's move on to Section 2, the 5-day BOD test.
So this is the industry standard BOD5 test. It's a highly controlled biological assay. Basically, you take a specialized 300 milliliter glass bottle, fill it up with your water sample, and measure the initial dissolved oxygen. Then you seal it tight, it has to be perfectly airtight, and pop it in an incubator at exactly 20 degrees Celsius for 5 days. Why 5 days? Simply because it takes time for the bacteria to actually consume the waste. Also, notice the protocol says it must be kept in the dark. This is a crucial detail. If any light gets into that bottle, algae in the water might undergo photosynthesis and actually produce oxygen, and, that would totally ruin our measurement of how much oxygen is being consumed.
If all this lab chemistry feels a little abstract, I want you to keep this really simple visual analogy in mind. Imagine the bacteria in our little glass bottle are a fire. The organic waste, the sewage, the pollution, that's the wood. That's the fuel for the fire. And the dissolved oxygen, that's the air keeping the fire burning. Obviously, the more fuel you throw on, the bigger the fire grows, and the more air it consumes. So our whole goal with the BOD test is to measure exactly how much air was used up over those 5 days to figure out how much fuel was sitting in the water.
All right, Section 3, the $0 rule. This is really the crux of the whole thing.
According to the standard methods that literally all accredited labs have to follow, a valid BOD test must maintain an absolute minimum residual dissolved oxygen level of 1.0 milligrams per liter by day 5. If you open up that bottle after 5 days and the oxygen has dropped below 1.0 or hit 0, the test has officially failed. Period. So, why is a reading of 0 totally useless to a scientist? Well, let's jump back to our fire analogy for a second. If you put a lid on a jar that has a fire inside and the fire burns up every last bit of air, it suffocates and goes out. But, and this is the absolute key point here, there might still be a bunch of unburned wood left sitting in that jar. It's the exact same thing in our test. If the oxygen in our BOD bottle drops to 0, the bacteria suffocate and starve. The biological reaction just stops prematurely. Sure, we know the pollution demand was high enough to wipe out all the oxygen, but we have absolutely no clue how much organic waste is actually left in the bottle. Because of that, we literally cannot calculate the true total oxygen demand.
And because of this, environmental regulators do not mess around. Based on guidance from places like the Pennsylvania Department of Environmental Protection, if that residual DO falls below the 1 milligram per liter threshold, the lab cannot report the calculated number as a definitive fact. They actually have to flag the data and report it as a greater than value. Because the oxygen ran out, the lab is basically waving a red flag to regulators saying, look, we know the pollution level is at least this high, but it's probably way, way worse. The fire ran out of air before we could measure all the fuel.
Now look at this actual laboratory documentation. What we're seeing here is an ultimate BOD test, which tracks oxygen consumption over a much longer stretch than just 5 days. If you follow the columns tracking the dissolved oxygen, the DO in milligrams per liter, you can see it steadily dropping over time. It goes from 8.1 down to 5.6 down to 3.5. When it gets dangerously low, the scientists actually have to step in and re-aerate the sample. They literally add more oxygen back in just to keep the bacteria alive so they can finish measuring the total waste. I think this perfectly illustrates why that 1.0 milligram per liter limit is so absolutely critical. You have got to keep the bacteria breathing if you want an accurate count of the pollution.
Which brings us to our final part, Section 4, Troubleshooting Test Failures.
You know, BOD is an inherently tricky biological assay. It's not just a simple push a button and get a number kind of test. The most frequent mistake that causes one of these 0D failures is choosing the wrong dilution factor. Think about it. If you suspect the water is highly polluted, you can't just fill the bottle with 100% wastewater. The bacteria would gorge themselves and deplete the oxygen in a matter of hours. You have to dilute the sample with pure oxygenated water. If your math is off and you put in too much wastewater, you'll overwhelm the oxygen supply way before the 5 days are up. Other common culprits? Poor bacterial seed quality, maybe a poorly calibrated DO meter, or, get this, even trapping a tiny little air bubble under the glass stopper. That one bubble would secretly leak extra oxygen into the water and completely ruin your final calculation.
I want to leave you with this somewhat provocative thought. We've spent this whole explainer geeking out over the incredibly strict rules of a 300 milliliter glass bottle sitting in a dark, 20-degree incubator. But remember what that little bottle actually represents. If a small, controlled sample of untreated wastewater can completely obliterate its own oxygen supply in just 5 days, imagine the devastating scale of that reaction when thousands of gallons of untreated waste flow into a real-world river. These lab rules we've been talking about, they aren't just bureaucratic red tape. They are the exact mathematical measurements of a water body's ability to sustain life. Ultimately, understanding the limits of oxygen in a bottle is exactly what helps us protect the oxygen out there in our world.